Welcome to the Deep Dive, where we cut through the noise and get straight to the insights that reshape how you see the world. Think about the last time you bought something manufactured in another country. Maybe a t-shirt you love, a new piece of tech that arrives seemingly overnight, or even that indispensable morning coffee. We often take for granted the incredible, complex journey that product makes, from its origin thousands of miles away right to your hands. We might consciously factor in the obvious costs like shipping fees or even import tariffs. But what if I told you there are far deeper, often hidden complexities, costs, and even fundamental inconveniences built right into the very structure of global trade? Costs that go far beyond just a transit fee or an import tax. Okay, let's unpack this. Today, we're taking a deep dive into something truly counterintuitive and deeply insightful, a concept the researchers call the geometry of inconvenience in trade networks. For a long time, we've operated on the assumption that global trade, like water, always finds its simplest, most efficient path, naturally flowing where it's cheapest and easiest. But today, we're exploring how the structure of trade costs, the way these burdens are arranged across different countries, can lead to some truly surprising and even what the paper called perverse outcomes in the global economy. This isn't just about what you ship, it's profoundly about what arrives and how the very architecture of that journey can warp the entire system in ways we never anticipated.
What's truly fascinating here is how cutting-edge mathematical models are revealing that the very design, the very topology of our global trade relationships can lead to scenarios where not everyone benefits equally, and perhaps more strikingly, some actors might actively seek what economists call rents.
Right, profit without creating new value.
Exactly. Profit without creating new value at the expense of overall global welfare.
We're going to illuminate how this intricate geometry dictates not just what happens in international trade, but profoundly why it matters for crafting effective policy, for ensuring economic stability, and even for your understanding of the deep, often invisible forces shaping globalization today. It's truly a new, powerful lens through which to view the global economy. And to guide us through this complex but incredibly insightful territory, we're drawing our insights from a truly groundbreaking recent research paper. It's titled The Geometry of Inconvenience and Perverse Equilibria in Trade Networks, authored by Michael Koopman, Austin Jacobs, Henry Pascoe, and J.E. Pascoe. This paper isn't just abstract theory. It rigorously builds on established economic models, but introduces a sophisticated, novel mathematical framework to understand international trade in a whole new light. Get ready, because it's going to challenge how you think about global commerce. So let's start with the absolute basics, the bedrock of international trade. It's inherently costly. When you think about international trade, we're not talking about simply putting a product on a ship and it magically appearing on the other side of the world for free, pristine, and intact. The paper emphasizes this core idea. International trade is never without its burdens, its frictions, its inconveniences.
Yeah.
Imagine a fruit producer in South America shipping 1,000 units of delicate berries across an ocean. Due to spoilage during a long transit or perhaps rough handling that causes breakage, maybe only 900 units actually arrive at a European port in usable, sellable condition.
Right, a real loss.
Or consider geopolitical factors. Economic sanctions that outright ban direct trade between two nations, forcing goods to travel circuitous, expensive, multi-leg routes through third countries. Then, of course, there are the more obvious but still significant costs like customs duties, tariffs, and administrative fees associated with crossing borders. It's a vast, intricate web of friction.
That's a perfect way to put it. And in economic models, these costs aren't just a vague notion, they're formally captured. The paper uses a concept called the freeness of trade function, or more broadly, a freeness of trade matrix, denoted as the Greek letter phi.
Phi, okay.
This same matrix quantifies the amount of a good that actually arrives at its destination for every unit shipped. So if you send one unit from country I to country J, you expect AG units to arrive.
Right.
For example, if II is just 0.8, it means only 80% of what you send makes it. The other 20% is lost to these various frictions, whether it's spoilage, breakage, or administrative hurdles.
Okay.
This matrix has specific mathematical properties that reflect real-world trade realities.
Yeah.
For instance, the value of each individual I, phi I, must be between 0 and 1, where 1 means perfect, cost-free trade with no loss, and anything less signifies some degree of loss or cost. It's also symmetric, generally meaning the loss from country A to country B is the same as from B to A. There's also the property of transit loss, which simply means if you trade from I to J and then J to K, the amount arriving at K isn't necessarily more than if you went direct, and typically less, because each leg incurs its own friction.
Makes sense.
And of course, self-trade is always one. You don't lose goods trading within your own borders, at least not in this context. It's a truly powerful and elegant way to model these real-world frictions.
Now, this groundbreaking paper builds on a crucial starting point, a highly influential model developed by Masi and Tabucchi in 2015. Many traditional trade models simplified things by assuming factor price equalization.
Right, the idea that wages and stuff eventually evens out everywhere.
Exactly. Which, as you can imagine, isn't quite how the dynamic, messy real world works for long. What made Masi and Tabucchi's model so important, and why it was a crucial foundation for this new research, is that it bravely didn't make that simplification. It allowed for real-world differences like varying country sizes and, crucially, heterogeneous trade costs, meaning the cost of trade wasn't uniform between all pairs of countries. It could be significantly higher or lower depending on the specific trading partners.
Precisely. The Masi and Tabucchi model draws its lineage from Paul Krugman's seminal three-country model from 1980, which, like many others in this field, sought to understand fundamental trade patterns. But Masi and Tabucchi pushed it further, allowing for much greater realism. Their model stands out because it uniquely allows for what they called size, neighboring, price, and integration effects of market liberalization.
Okay, so it captures a lot more real-world stuff.
Yes, exactly. This means it can account for how the sheer size of a country impacts its trade flows, how geographical proximity matters, how prices fluctuate across borders, and how different integration policies like trade agreements or liberalization efforts affect market outcomes. And here's the truly crucial part for their original work and for our story today. For a three-country model, where n, the number of countries, equals 3, they rigorously proved that a unique equilibrium exists.
A single, stable outcome.
A single, stable outcome. This meant that, given their model's parameters and these heterogeneous trade costs, there was one clear, stable, predictable outcome for trade patterns. This was a profound finding. They even speculated that this elegant result, this unique equilibrium, might generalize to models with more than 3 countries.
Ah, okay. So they thought maybe the simple result holds even when things get more complicated.
That was the speculation, yeah. This formed a kind of foundational assumption for much of the field, suggesting that even in more complex scenarios, the global trading system would naturally settle into a single predictable state.
This is where it gets really compelling because the paper we're diving into today fundamentally questions that very assumption, that long-held speculation. If Masi and Tabucchi found this elegant, stable world for 3 countries, the big question for this new research was, does that stability hold when you scale up to a truly global network encompassing many more nations?
Right. What happens with, say, 5, 10, 100 countries?
And the answer, as we're about to discover, is a resounding not always, leading to some truly counterintuitive and quite unsettling outcomes.
This is precisely the breakthrough that the Koopman, Jacobs, Pascoe, and Pascoe paper delivers. The new research, leveraging advanced mathematical tools like spectral theory, which, simply put, is like finding the unique fingerprint of a network, examining its fundamental properties through numbers called eigenvalues.
Okay, eigenvalues, like a network signature.
Kind of, yeah. It proves that for n, the number of countries greater than 4, the Masi and Tabucchi results do not always generalize. Instead of a single, unique, predictable outcome, the models can actually admit multiple equilibria, sometimes as many as 3. And crucially, these aren't just different paths the system could take. They are what the authors term perverse equilibria.
Perverse equilibria. That's a strong, evocative term. It doesn't just mean there are multiple ways things can turn out. It implies that these outcomes are actually detrimental to general welfare, meaning they lead to a worse overall situation for many, even if some benefit. And a key element of these perverse scenarios, as you mentioned, is something called rent-seeking. For our listeners, can you quickly explain what rent-seeking is in this context and why it makes an outcome perverse?
Certainly. In economics, rent-seeking refers to activities that benefit an individual or a group by extracting existing value from the system, rather than by creating new wealth or making the pie bigger.
Okay, so not making things better, just grabbing a bigger slice.
Precisely. Think of it like this. If you have a perfectly competitive market, firms innovate, produce efficiently, and offer better goods or services. Rent-seeking, however, is about using political or economic influence to manipulate the environment, to rig the game, if you will, to gain a disproportionate share of existing resources. It's essentially taking a slice of the pie that you haven't helped bake, and often in doing so, you actually shrink the overall pie for everyone else by introducing inefficiencies. In the context of these perverse equilibria, it signifies distributional conflict at the cost of general welfare. This means that certain actors, countries, firms, even individuals benefit immensely, often disproportionately, by exploiting these systemic inefficiencies. They profit not necessarily by being more productive or innovative, but by strategically positioning themselves to extract value from others. The paper specifically highlights that in these scenarios you can see runaway inequality in terms of utility, wages, and the distribution of resources across the network.
Runaway inequality, wow.
Yeah, it's a situation where some thrive not by creating more overall economic value, but by strategically positioning themselves to extract more from others in a less efficient system.
That sounds like it's tied to a very specific kind of network structure, like not just any random arrangement of trade costs. And the paper introduces a concept to describe this critical structure, something called anti-blocks. Can you walk us through what an anti-block is in this context? Because it seems central to understanding these perverse outcomes.
Yes, the concept of anti-blocks is indeed central to understanding precisely when and why these perverse equilibria emerge. Imagine the world countries divided into two distinct groups, or blocks.
Okay, two groups.
The defining characteristic of an anti-block configuration is that countries within a given block have very little, or crucially, no direct trade with each other. Instead, their trade ties are primarily, if not exclusively, directing towards countries in the other anti-block.
So Group A only trades with Group B, and Group B only trades with Group A. No internal trading within A or B.
Exactly. You have two groups, and they only trade across the divide, never within their own group. The paper notes that such arrangements can arise for various reasons, including political factors, historical animosities, or even deeply ingrained geographical realities that make direct internal trade prohibitively costly. For example, a group of politically aligned nations might intentionally restrict trade among themselves to isolate an adversary, or a set of landlocked countries might be forced to trade only through a select few transit nations. It's these specific configurations, characterized by the formation of these anti-blocks, where the structure of non-trade is as important, if not more so, than the structure of trade itself, that makes a trade network susceptible to these perverse equilibria.
Ah, okay. So it's about who you don't trade with just as much as who you do.
Precisely. It's not just the simple presence of trade costs, but how those costs are distributed and how they partition the global trading system into these isolated yet interdependent groups. And what's crucial here is that this discovery has significant substantive applications to economic sanctions, which, as we'll discuss in more detail later, are a prime example of policies that can deliberately create these very geometries of inconvenience.
So we're talking about geometry, which sounds like we're drawing shapes and measuring distances. How do we translate complex international trade with all its nuances of goods and money flowing between countries into something that can be analyzed geometrically? How do they visualize this?
That's where the elegance of graph theory comes in, simplifying complex relationships so they can be mathematically analyzed. Think of countries as vertices or points on a map, and the trade routes or connections between them as edges or lines linking those points.
Okay, countries are dots, trade routes are lines. Simple enough.
Pretty much. This forms a network, just like a social network or a transportation network. For instance, a complete graph, denoted as AN, represents a scenario where every country can trade directly with every other country. It's the ideal of maximum possible connections, like a fully interconnected global economy. But the critical structure for understanding anti-blocks and the paper's findings is the bipartite graph, denoted as KNM.
Bipartite, like two parts.
Exactly. Here, the entire set of countries, or vertices, is divided into two distinct and separate groups. Let's call them Group V1 and Group V2. The crucial rule is that trade only occurs between a country in V1 and a country in V2. There's no trade within V1 and no trade within V2.
That's the anti-block structure again.
Precisely. This mathematically is the precise representation of those anti-blocks we discussed earlier, where you have two groups that don't trade amongst themselves, but trade exclusively with the other group. You can conceptualize this visually, much like Figure 1 in the paper, which shows a simplified drawing of a complete graph versus a bipartite graph, clearly illustrating this division. And of course, for a country to even matter in these models, it has to be connected. It must have trade relations, directly or indirectly, with at least one other country.
That makes intuitive sense. But trade isn't just an on or off switch, a simple connection. Some connections are stronger, easier, or less costly than others. This is where weighting comes in, giving value or friction to those lines connecting the countries.
Precisely. We move beyond simple adjacency to capture the real-world complexity of trade costs. In weighted graphs, each edge or connection is assigned a numerical value, or weight.
Like how strong the connection is.
Yeah, or how weak, depending on how you look at it. First, there's the freeness of trade matrix, or E, which we touched upon earlier. Here, the weight for each connection is a value between 0 and 1, representing the percentage of value that's preserved in transit. If CHACH is 0.9, 90% of the value arrives, 10% is lost. The properties we mentioned earlier, symmetry, transit loss, perfect self-trade, are key here. But there is an alternative, equally useful way to weight these connections, and that's through a distance matrix or friction of trade metric.
Okay, distance or friction. Sounds like the opposite of freeness.
It is, mathematically. It's derived from the freeness of trade matrix by taking the negative logarithm of each yi, so may, ner, log, ik. This essentially transforms freeness into a measure of difficulty or inconvenience.
Got it. Higher number means more friction.
Exactly. The higher the number in me, the harder or more costly it is to trade between those two countries. This me metric also has important mathematical properties that align with our everyday understanding of distance. It's always non-negative. You can't have negative inconvenience. The distance from a country to itself is 0. It's symmetric. The inconvenience from A to B is the same as B to A. And crucially, it satisfies the triangle inequality, meaning the direct trade cost or inconvenience between two countries is always less than or equal to the cost of trading through an intermediary.
Right. The direct route is never longer than going via somewhere else.
Pretty much. This truly captures the essence of inconvenience in a measurable way.
So we've got this concept of Massey-Tabuchi stability, which seems critical. It refers to a condition where a unique, predictable equilibrium is guaranteed, like a well-behaved economic system. But how does this stability connect to all this talk of matrices, graphs, and these mathematical distances you're describing?
It's a beautiful and profound connection. And it's where the cutting-edge math comes in to reveal the underlying mechanisms. A freeness of trade matrix is considered Massey-Tabuchi stable if a related mathematical construct derived from it remains positive semi-definite for all relevant trade conditions.
Okay, positive semi-definite. That sounds technical.
It is a bit technical, yeah. But think of it like this. Imagine a perfectly balanced scale or a very stable, well-oiled machine. A positive semi-definite matrix means the system is fundamentally stable, like a well-behaved mechanism where every action leads to a predictable, beneficial, or at least non-destructive outcome.
So mathematically stable means economically stable, one outcome.
That's the essence of it. It's the mathematical way of saying things work as they should, leading to a single, unique equilibrium. Crucially, the paper leverages a fundamental result from mathematics called Schoenberg's theorem to link this Massey-Tabuchi stability directly to the friction of trade metric we just discussed.
Schoenberg's theorem.
This theorem essentially says that a trade network is Massey-Tabuchi stable if and only if its corresponding friction of trade metric can be mapped to actual, measurable, squared Euclidean distances between points in some geometric space.
Wait, so if the trade inconvenience acts like real distance on a map?
That's a great way to think about it, like being able to represent all your trade inconveniences as if they were actual physical distances on a map. If your trade network could be represented this way, in this kind of metric cone, which you can imagine as a complex map where every point inside represents a different way our global trade network could be structured, then your system is guaranteed to be stable and have a unique equilibrium. It's an elegant mathematical condition for economic harmony.
So the stability comes from being able to map these trade frictions to distances in a very specific, almost intuitive way. But then, as you hinted, the paper makes a stunning revelation about what happens when that mapping breaks down, when instability takes over.
Yes, here's where it gets truly impactful, because this is the core finding that challenges a long-held assumption. If we connect this to the bigger picture, the paper rigorously proves that for bipartite graphs, those anti-block structures we talked about, where the total number of countries n is greater than or equal to 5, and each anti-block has at least 2 countries, meaning you have at least 2 in one isolated group and 2 in the other, the trade network is not Massey-Tabuchi stable.
So the anti-block structure itself causes instability, mathematically.
Precisely. This is a direct contradiction to the original speculation that unique equilibria might generalize to more countries beyond 3 or 4. Instead, for these specific configurations of fragmented trade, unique equilibria are not guaranteed. The researchers even discovered a precise mathematical fingerprint or formula that tells us exactly when this stability collapses. It's directly tied to the sizes of those two anti-blocks, revealing how bigger or smaller groups of isolated trading partners affect the system's overall health.
So the math pinpoints the problem structure.
Exactly. When this formula meets certain conditions, it indicates that the stable, single equilibrium disappears, making way for multiple, less desirable outcomes. You can visualize this with conceptual diagrams, much like Figure 2 from the paper, which illustrates a K3-2 graph, meaning 3 countries in one anti-block and 2 in another. This clear mathematical proof lays the groundwork for understanding why perverse, chaotic, or exploitative outcomes can emerge from what seems like a simple trade network.
So the math clearly shows us when stability breaks down in these anti-block structures. But how does that mathematical breakdown translate into those perverse outcomes? What's the specific mechanism the paper identifies that pushes the system towards runaway inequality or rent seeking?
This brings us to the conditions for non-unique solutions, which are those perverse equilibria. The paper demonstrates that if certain mathematical conditions are met, specifically related to the eigenvalues, those unique numbers that act as the network's fingerprint of the freeness of trade matrix, then the uniqueness of the solution is lost.
Right, the eigenvalues again.
Yes. This is the mathematical threshold, where the system can tip from a single stable outcome to multiple less desirable ones. When these conditions are met, the economic forces no longer push towards one efficient state. To illustrate, the paper discusses a 6-country example, a specific bipartite network where this condition can be met. In such a scenario, the model predicts that solutions for wages, utility, and resources can become approximately a 0-1 vector.
A 0-1 vector, what does that mean practically?
What this means in practical terms is runaway inequality. Resources, wealth, and welfare become highly concentrated in one part of the bipartite network, while the other parts are significantly disadvantaged, almost to zero.
Wow, so like all the benefits go to one side of the anti-block divide.
Pretty much. So the mathematical instability directly translates into a situation where some parts of the network accumulate wealth and power, not necessarily through productive means, but through the exploitative nature of these perverse equilibria. They're essentially cornering the market on trade itself, becoming indispensable intermediaries.
Now, let's transition from these abstract mathematical models and graph theory to a very tangible, highly relevant, real-world application: economic sanctions. They're constantly in the news, designed to impose economic pain and make trade difficult for targeted nations. How do these sanctions, which drastically reduce direct trade, create the very geometry of inconvenience that the paper describes as leading to perverse outcomes?
This raises an important question, doesn't it? How do economic sanctions, which are explicitly designed to drastically reduce or even prohibit direct trade between senders and targets, contribute to these perverse equilibria? The answer is that sanctions are, in essence, policy tools that can deliberately and effectively establish those anti-blocks we discussed earlier.
So sanctions create the anti-block structure.
They absolutely can. You can think of one block as comprising the sanctioning states and the targeted states, which by design have very limited or no direct trade between them. This is the inconvenience being imposed. The other block then consists of sanctions busters, third-party countries, entities, or even specific firms that step into the void and act as intermediaries, facilitating trade between the two otherwise isolated groups.
Right, the middlemen who find a way around the rules.
Exactly. This creates the exact bipartite structure that the mathematical models identify as susceptible to perverse outcomes. The targeted country must use the buster, and the sanctioning country's firms often must use the buster if they want to access that market, even indirectly.
And these sanctions busters, they're often commercially motivated, right? They're essentially exploiting these distortions created by the sanctions to their own benefit. It sounds like they're the ones extracting the rents you mentioned earlier.
Precisely. Sanctions busters are very often commercially motivated, identifying a highly lucrative opportunity in the severe market distortions created by the sanctions regime.
Makes sense. There's money to be made in the gaps.
Absolutely. By acting as the necessary intermediary, they can extract significant rents from both the sender and the target states. They essentially become the exclusive toll booth on a newly created, less efficient, and often more expensive trade route, benefiting handsomely from the inconvenience they facilitate. The paper provides compelling, real-world examples. Think of the United States sanctions on Iran. where the United Arab Emirates has often acted as a key sanctions buster, providing a vital conduit for goods and funds.
Okay, I remember hearing about that.
Or, historically, during the Cold War, U.S. sanctions on apartheid South Africa, where the United Kingdom often played a similar intermediary role, allowing British firms to continue trade. What's particularly striking is that these intermediaries might even publicly support the sanctions, maintaining a facade of compliance, while quietly facilitating trade for their own domestic firms, directly profiting from the very inefficiencies the sanctions create.
Wow, so playing both sides almost.
In a way, yes. It's a powerful illustration of how the geometry of inconvenience creates private gain at collective cost.
That's a fascinating nuance. So it's not just about how many sanctions busters there are in total or even their individual commercial motivations. It's also about how they interact with each other.
What's truly fascinating here is that the paper suggests the ability of these sanctions busters to seek and extract rents is significantly tempered if they have low-cost trade among themselves.
Wait, so if the busters can trade easily with each other, they make less money from the rent seeking.
That's right. In other words, if the intermediary states can easily and cheaply trade with one another, it creates a degree of internal competition within that anti-bloc, which reduces their individual leverage to extract maximum rents. If one buster charges too much, the target or sanctioning firm can simply go to another buster who has easier access to goods from the first. So rent seeking is most severe, and the perverse outcomes are most pronounced when multiple sanctions busters are relatively isolated from each other when they form their own anti-bloc of non-trade.
Okay, so if the middlemen can't easily work together or compete, that's when they can really exploit the situation.
Exactly. This implies a very counterintuitive yet critical policy insight. Fostering trade between these sanctions-busting states might actually help curtail their rent-seeking behavior and, paradoxically, improve the overall efficacy of the sanctions regime by reducing the perverse incentives and reintroducing some competition.
That is really counterintuitive. Helping the sanctions busters trade with each other helps the sanctions work better. Sort of.
It's about breaking down the internal anti-bloc structure of the intermediaries themselves, making them less exclusive gatekeepers.
This definitely challenges some common assumptions about sanctions effectiveness, doesn't it? Especially when we talk about the debate between bilateral versus multilateral sanctions, which is often framed as the more countries sanctioning, the better.
Absolutely. The paper provides crucial theoretical nuance to long-standing debates about sanctions. For instance, in the case of bilateral economic sanctions, where one country sanctions another, if there are only one or two sanctions busters acting as intermediaries, perverse equilibria may not even exist. The system might remain stable.
Okay.
However, if there are three or more sanctions-busting states, depending crucially on the ease of trade between them, perverse equilibria may emerge.
So the number of busters matters, but also how they connect.
Yes. Now consider multilateral sanctions, where multiple states are coordinating to sanction a target. If there is only one sanctions-busting state acting as an intermediary for all of them, the model suggests no perverse equilibria exist. But if there is more than one sanctions-busting state, and especially if those busters don't trade easily among themselves, then again, perverse equilibria may arise. This highlights a previously unidentified and incredibly important interaction. It's not just about the absolute number of sanctioning states or the number of targets, but a complex interplay between the number of sanctioning states and the number of sanctions busters, and critically, their internal trade relationships. The paper also has new implications for situations where multiple states are targeted simultaneously. This is a growing trend in modern foreign policy, with more and more states facing coordinated economic pressure.
Right, like group sanctions.
Exactly. Our results suggest that the more states that are targeted simultaneously by sanctions, the more likely perverse equilibria are to exist, precisely because it's easier to create these large, insulated anti-blocs of non-trade. Furthermore, these inefficiencies and rent-seeking opportunities, once established, can create powerful vested interests. They can persist even after sanctions are officially lifted, as the new, distorted trade patterns become entrenched and incredibly difficult to displace.
So the damage can last long after the policy ends.
It creates a sticky, inefficient legacy that can linger for years, even decades.
Okay, let's unpack this further. If this geometry of inconvenience dictates economic outcomes in such profound ways, leading to these potentially perverse and undesirable results, can policy changes actually alter that geometry to achieve more favorable results? Can we use this understanding to craft more effective policy interventions rather than just stumbling into unintended consequences?
That's the million-dollar question, and it's where the paper takes a truly proactive turn. The researchers tackle it head-on by using numerical simulations to illustrate precisely how changes in trade structure, whether they arise from deliberate policy decisions or from unforeseen external shocks, can influence Mase-Tabuchi stability and thus determine whether unique, beneficial equilibria or multiple, perverse equilibria prevail. They employ a fascinating visualization technique using triangles. Imagine a geometric space, a cone as they call it, where every single point inside it represents a different way our global trade network could be structured.
Okay, a map of possible trade networks.
Exactly. Each vertex of this triangle represents a specific extreme configuration of a trade network, what they call an extreme ray in this mathematical metric cone. Every point within that triangle then represents a weighted average of these extreme network configurations. When they color these points, blue indicates Mase-Tabuchi stability, meaning a unique, non-perverse equilibrium is guaranteed. Red signifies instability, where perverse equilibria are possible.
So blue is good, stable, red is bad, unstable, perverse outcomes possible.
That's the basic idea. This allows them to graphically show the impact of moving from one trade network structure to another, providing a visual map of stability.
So this mapping tool allows them to play out what-if scenarios. Let's walk through some of these specific policy scenarios the paper simulates, starting with what happens if one state unilaterally erects trade barriers or essentially just cuts itself off from trade with a specific group of countries, or even tries to leave an existing anti-bloc. What does the geometry tell us about that?
It's not straightforward, and the answer highlights the crucial, often counterintuitive role of network structure. Let's look at what Figure 3 from the paper conceptually illustrates, comparing three types of networks. One state removed from an anti-bloc, a bipartite network with 4 states in one block and 2 in another, K4-2, and a balanced bipartite network with 3 states in each block, K3-3. The simulation shows that if you remove one state from the smaller anti-bloc, for example, in a network like a K4-2, if one of those 2 countries completely severs its trade ties with the other bloc and effectively leaves the network, it can induce Mase-Tabuchi stability.
Removing someone from the small group helps stability.
It can, yes. It literally shifts a large portion of the network from a red, unstable zone to a blue, stable one in their simulation. However, if you remove a state from a larger anti-bloc, as the simulation for a K3-3, 3 in each block, shows, it may not fundamentally change the stability. The network can remain stubbornly in an unstable red region, even with one less participant. Figure 4 further reinforces this critical insight. If the cut is from the larger anti-bloc, say, a state from the larger group in a K4-2 network completely exits the international trade network, perverse equilibria can still persist across a wide range of trade friction levels.
So pulling out of the big group doesn't necessarily fix the instability.
Not necessarily. The key takeaway from these simulations is that the location of the cut, the specific part of the network where trade ties are severed, matters immensely. If you consider the left-hand side anti-bloc as sanctions busters, for example, convincing just one of them to stop sanctions busting may not be pivotal to the efficacy of the sanctions if there are many others still operating, or if that buster was part of a larger, more resilient bloc.
Right.
Conversely, if the left-hand side anti-bloc represents sanctioning states and targets, one sender or target pulling out of the trade network may not fundamentally shift the system if they are part of a larger, more resilient anti-bloc structure. It's about how the cut affects the overall balance and fragmentation of the anti-blocs.
That's a subtle but absolutely critical point. What about a more sweeping policy change like universal trade barriers or essentially isolationism? What if every country just puts up tariffs against every other country? Sounds like a recipe for global economic disaster, but what does the geometry tell us?
Interestingly, the geometry offers a surprising perspective. If every state adds uniform barriers to trade with every other state, a scenario that pushes the network towards what the paper calls the discrete metric, where every point is uniformly separated in terms of trading convenience, this can actually force the entire network into Mase-Tabuchi stability.
Wait, everyone putting up walls makes things stable.
According to this geometric model, yes. You see this vividly illustrated in Figure 5. It shows that, as a network-wide strategy, universal barriers can be a perfectly viable option for achieving stability and preventing perverse equilibria.
That is so counterintuitive.
It is, because our usual economic intuition screams against universal protectionism. But in the context of these complex geometries of inconvenience, it can effectively remove the precise structural conditions that allow for rent-seeking and runaway inequality. It prevents a formation of those advantageous intermediary positions. The inverse is also true and equally fascinating. Universal technological advancements that dramatically lower trade costs across the board, if they're shared by all trading partners, could have the opposite effect.
So making trade cheaper for everyone could make things unstable.
It could, according to the model.
Yeah.
They might push a previously stable network into an unstable one by making it easier for those specific anti-block structures to emerge and for the conditions for perverse equilibria to be met. It's a powerful reminder that it's not just about the absolute level of costs, but how those costs reshape the underlying geometry of connection and non-connection. Universal freeness doesn't necessarily mean universal stability.
So it's not just the magnitude of the barrier, but crucially where it's placed within the network that's pivotal. Let's dig into that asymmetry a bit more.
Figure 6 perfectly illustrates this crucial asymmetry. It compares two structurally similar bipartite networks, K24 and K42. These are essentially mirror images. K24 has 2 countries in one anti-block and 4 in the other, while K42 has 4 in one and 2 in the other.
Okay, just swap sides.
Right. The simulation shows that a unilateral increase in trade barriers, what they call a cut, meaning one country decides to severely restrict its trade with the other bloc, is pivotal to inducing Mase-Tabuchi stability when the state making that cut is part of the smaller anti-bloc.
Cutting ties from the small group has a big impact.
A big impact on stability, yes. For example, if it's one of the 2 countries in the size 2 bloc, that single cut from the smaller side is enough to fragment the network in a way that disrupts the conditions for instability, pushing it into the stable blue zone in their simulation. However, that exact same unilateral cut does not induce stability when the state is part of the larger anti-bloc, say one of the 4 countries in the size 4 bloc.
Cutting ties from the big group doesn't do much for stability.
The larger bloc can absorb the change without fundamentally altering the network's problematic geometry, it seems. If we connect this to the bigger picture, this is perhaps the most significant policy implication. Broad, sweeping statements about bilateral versus multilateral sanctions, or simply counting the number of sanctions busters, entirely miss the crucial point.
It's all about the shape of the network.
Exactly. The network geometry of international trade is central to understanding the true impact of any policy intervention. It's not just about who trades with whom, but about the specific structural relationships and, critically, the non-relationships, those deliberate or incidental anti-blocks that shape the entire system. Understanding this geometry is paramount for effective policy design.
This is a truly profound shift in perspective. Moving beyond the immediate economic implications and the specific case of sanctions, how does this research, this geometry of inconvenience, challenge our broader understanding of things like globalization backlash, which we've seen so much of in recent years?
It offers a powerful and novel lens. Traditionally, globalization backlash, the political and social resistance to increased global integration, has been primarily understood as a reaction to distributional consequences.
Right. The winners and losers argument.
Exactly. The idea that some people or sectors win from increased trade while others lose, and that redistribution mechanisms are imperfect or insufficient. But this paper suggests a distinct complementary logic. Globalization backlash might also be a reaction to the ill effects of more extensive, cheaper trade in partition systems, which precisely describes these anti-blocks and the increased opportunities for rent-seeking they create.
So people might be reacting against the unfairness enabled by these weird network structures.
That's the idea. This suggests that some political opposition to more extensive trade with status quo trade partners, manifesting as support for things like border walls, protectionist tariffs, or a general distrust of global supply chains, might not just be an inherent anti-trade stance. It could be an implicit, perhaps even unconscious attempt to undermine or disrupt these underlying bipartite trade structures that facilitate rent-seeking and concentrated power, even if the proponents of these policies don't frame it in those terms.
Trying to break the bad geometry without realizing it.
Perhaps. They're trying to change the geometry, perhaps instinctively, to escape its perverse outcomes.
And can we see historical parallels for this concept? Are there examples from the past where this geometry of inconvenience might have played a hidden yet powerful role?
Absolutely. The mercantilist trading networks prevalent during the colonial era offer a prime historical illustration. Colonizers deliberately structured trade relations to restrict direct trade ties for their colonies, forcing them to primarily use the colonizer as an intermediary.
Right, the classic colonial model. Colonies trade only with the mother country.
Exactly. So you had colonies in one anti-bloc, the colonizer in another, and they only traded through that central power. The paper points out that colonies that were strategically positioned to act as intermediaries within these networks, perhaps they were a transshipment hub or had special access, often thrived, precisely because they could extract rents from both sides.
Okay, so some colonies benefited by being the middleman within that system.
Yes. In stark contrast, those colonies forced into a dependent anti-block structure where they had to trade almost exclusively through the colonizing country and were forbidden from trading with nearby partners, often languished economically. This wasn't just about economic profit for the colonizers. They reaped what the paper calls political rents. By deliberately shaping the structure of international trade, controlling the very geometry of convenience for their own benefit.
Controlling the network itself was a source of power.
Precisely. This neatly connects to the concept of the extensive margin of trade, meaning the specific trade ties that are restricted or enabled, versus the intensive margin, which is simply the volume of trade. It shows how the design of the network creates profound economic and political consequences. This framework also offers new insights into the enduring, often underestimated, role of geography in international trade. Landlocked states, for example, often embody this geometry of inconvenience in a very natural way.
Yeah, that seems obvious. They have to go through neighbors.
They do. To access global markets, they must conduct trade through transit countries. If these transit countries are also relatively isolated from each other, in effect, forming an anti-block with the landlocked state as the necessary intermediary between them and the global market perverse equilibria can easily arise. This often leads to consistently high logistics costs, systemic inefficiency, and a diminished share of the gains from trade for the landlocked nation. They're perpetually stuck in a position where others can extract rents from their necessity to trade.
So what does this all mean for how we approach international trade policy going forward? It sounds like the paper is suggesting a genuine paradigm shift, moving beyond our traditional focus.
It truly is a new paradigm. Traditionally, structural approaches to international trade have tended to focus on broad concepts like the distribution of state power, the economic size of nations, or simple trade volumes.
Yeah, like how big is China's economy? How powerful is the U.S. Navy?
Right, things like that. But this paper proposes a novel mechanism, the geometry of trade freeness, and powerfully demonstrates that this factor is central to understanding not just economic outcomes, but also broader political goals and the often unforeseen impacts of foreign policy. It moves us beyond standard network analysis that primarily focuses on metrics like network centrality or density. Instead, it offers a policy-relevant geometry of inconvenience, providing specific, actionable insights into how the very design of our trade networks or the deliberate imposition of inconvenience through policy can generate unforeseen and often detrimental outcomes.
So policymakers need to think like network architects, almost.
That's a good way to put it. It compels policymakers to think not just about individual trade barriers, but about how those barriers collectively sculpt the global trade landscape.
Yeah.
Hashtag tag outro.
Wow, what a deep dive. We started with the seemingly simple idea of trade costs, but thanks to this incredible research, we've seen how the pattern of trade, specifically these strategically isolated anti-blocks, and the resulting geometry of inconvenience, can lead to something called perverse equilibria. This isn't just abstract theory from a mathematical model. It has profound implications for understanding the true, often hidden costs of economic sanctions, for reevaluating historical trade patterns like mercantilism, and even for gaining a deeper, more nuanced perspective on the current attitudes towards globalization.
Yeah,
It's all about the underlying architecture of trade, not just the individual transactions themselves.
indeed. We have seen how, surprisingly, what might seem like a straightforward policy solution, like adding more sanctions or increasing trade barriers, can actually exacerbate problems and lead to unintended consequences if the underlying network structure isn't carefully considered.
Right, like that universal barrier thing being potentially stabilizing. So strange.
Exactly. The ability to understand not just what trade exists, but crucially how it's interconnected, or perhaps more importantly, not connected, is absolutely essential for crafting effective policy and achieving more equitable and efficient outcomes for everyone involved in the global economy. It's about seeing the invisible forces at play.
So the next time you hear about complex trade disputes, or the imposition of economic sanctions, or even heated debates about building more border walls, think about the unseen geometry at play. What hidden anti-blocks might be forming or solidifying, and how might that geometry of inconvenience be shaping the outcome in ways we don't immediately see or anticipate?
This raises an important question. In a world increasingly interconnected yet prone to fragmentation and strategic isolation, How can policymakers strategically foster new trade ties and connections to disrupt existing geometries of inconvenience rather than inadvertently creating more opportunities for rent-seeking and unintended perverse consequences?
Proactively designing better networks.
Exactly. It's about designing trade systems for collective benefit, not just managing existing flows.
We hope this deep dive has given you some powerful new tools to understand the complex and often counterintuitive world of international trade.